In the last video, we focused on fatty acids, which are molecules that have a carboxylic acid group, that is COOH, bonded to a long carbon alkyl chain of generally 12 to 20 or more carbon atoms. In this video, we follow up from that to focus on waxes. The way that waxes are related to fatty acids is that fatty acids are one of the reactants required to create waxes. We'll look at that chemical reaction a little bit later on in this video. But first, a reminder of some of the places where we encounter waxes, which are generally greasy solids at room temperature. Waxes are produced by beeswax in other words. Also, various waxes are produced by plants to give them their glossy coating on the leaves, which serves the purpose of protecting them from drying out and also acts as a protectant from other elements such as wind. Waxes are a major consumer product being found in things such as car wax, also in candles. Earwax is a naturally occurring wax produced by humans, and it's pretty wild to think that our genome encodes genes that catalyze reactions that create wax within our ears to serve an important function of protecting the ear. Let's take a closer look at how waxes are produced. Waxes are produced industrially in a variety of chemistry labs. They are also synthesized within our bodies and within plants, insects, and other organisms. And the way that these molecules are synthesized is analogous when done by living things and when done through industrial processes. The biggest difference between the synthesis of wax in living things and through industrial processes is that within living things, our catalysts are enzymes, which we'll learn about more in a later unit. In industry, catalysts are things such as acids. So let's take a look at the reaction that yields wax molecules, these greasy solids. The way that a wax is produced is it is the ester that results from a Fischer Esterification type reaction of a fatty acid and a long-chain alcohol. As a reminder of our Fischer Esterification, which we learned about in our unit on carboxylic acids and esters, Fischer Esterification is the reaction where we start with a carboxylic acid, which has our COOH group here. We react it with an alcohol, and in this reaction schematic, I'm abbreviating our carbon chain here as R in the carboxylic acid, and R prime is the carbon chain in the alcohol. So we react our alcohol with our carboxylic acid, which I'll abbreviate as Ca. The reaction of those two substances, catalyzed either by acid or by, in biological systems, an enzyme that provides the acidic group necessary for this reaction to take place rapidly. The O-alkyl group from the alcohol, OR prime, replaces the OH group from the carboxylic acid, as we learned in our Fischer esterification reaction. So those two essentially switch in the net chemical equation for this reaction. So that gives us a product where we have our original R group from the carboxylic acid bonded to our carbonyl, and then rather than having OH here, we have OR, where OR corresponds to the O-alkyl group of the alcohol reactant. So I'm going to put OR prime here to reflect the structure of the O-alkyl group that was bonded to the alcohol. The other product of this reaction is, through this reaction, we liberated OH from here. We also have a hydrogen here, so that gives us in total H2O. So I will also plug in water as a product of this reaction. I show this as an equilibrium reaction because, as we learned in the last chapter, this reaction can be reversed by applying Le Chatelier's principle to add an excess of one of the two reactants or to take away one of the two products to force the equilibrium toward the side of the desired product. So in the synthesis of wax, rather than this starting material here being a carboxylic acid that we typically think of as having a relatively short alkyl chain, instead, if the specific carboxylic acid that's used is a fatty acid, which is defined as having a long alkyl chain, generally of 12 to 20 or more carbon atoms. And the alcohol reactant R group as well features a long alkyl chain. What results is a pretty large product where this R group here, provided by the fatty acid, and the R prime group provided by the alcohol are both very, very long carbon chains. So we have a long carbon chain extending out this way and a long carbon chain extending out that way. And that is the reason why these molecules are solids and greasy at room temperature. They are greasy because they have these long alkyl chains on both sides. They are solids because of the fact that having not just one, but two long alkyl chains here and here creates a very bulky molecule that packs together very tightly and has strong intermolecular interactions that, due to those intermolecular interactions, the temperature must be raised quite high in order to disrupt those interactions and allow the phase transition from solid to liquid. So, in other words, or to write this down, due to the strong intermolecular interactions, those would specifically be van der Waals forces primarily because these are nonpolar chains. So due to those strong intermolecular interactions, these compounds are waxy solids at room temp. So let's now take a moment to apply what we've just learned about this reaction toward a real-world problem. This real-world problem of predicting the structure of a particular wax produced by the reaction of a 16-0 fatty acid with an unbranched primary alcohol that has the formula C30H62O is a real-world molecule that is one of the primary components of beeswax. In order to answer this problem, we have to remember what some of our key definitions were, like 16:0 fatty acid refers to a fatty acid that has a total of 16 carbon atoms. In my opinion, the easiest way to draw this structure, rather than doing a line angle formula, is to actually do a condensed structural formula in this case, where I'm going to place at one end my carboxylic acid group. Then I'm going to, in order to reach my 16 carbons in total that is required for a 16:0 fatty acid, I'm going to plug in CH2 because we have a long alkyl chain, and within that long saturated alkyl chain, we must have CH2 groups throughout. And then at the very end, we would have a CH3 group so that all of those carbons have a complete octet. Now to fill in this missing piece here with how many CH2 groups there must be, since this is 16-0 fatty acid, we've accounted for one of the carbons as the carbonyl, the other is the methyl, so that would leave us with 14 carbons left that we need to plug in. So I put CH2 14, and the fact that those carbons are in parentheses indicates that there are 14 CH2 groups there. That's going to be our 16-0 fatty acid. Then, our unbranched primary alcohol, we need to recall some of the terminology there. Unbranched meaning just a straight chain with no branches coming off of it. Primary alcohol refers to a carbon of the alcohol group has only one other carbon directly bonded to it, meaning that the OH group for this molecule must be at the very end of the chain. So we can go ahead and draw that out like so, and I'm going to do this as a condensed structural formula as well, because I think that's easier than drawing a zigzag line for a line angle formula as 30 carbons. So our OH group, being primary, would be bonded to a CH2, and then that CH2 is part of the start of a long line of CH2s. In fact, in order to have a formula that has 30 carbons total, we would need 29 CH2 groups followed by one methyl group, so that as a result, all of these atoms would have a complete octet. That gives us our formula C30H62O. Now from here, we were asked to predict the structure of the wax provided by this reaction. It doesn't indicate to us whether this is a biological reaction, which would be catalyzed by an enzyme, or an industrial reaction, which would be catalyzed by an acid. We're just asked to provide the product here, so we don't really need to know that information per se. In reality, this reaction can take place both biologically in beeswax production and industrially in the production of other waxes made synthetically that would be chemically identical to the natural molecule. So, taking a look at this structure and our template above, we recognize that the OH group of our fatty acid, right here highlighted in green, is going to be replaced with the O-alkyl group. That's our oxygen followed by the carbon chain here, highlighted in green, in our alcohol molecule. Now going ahead with plugging those together, I'm going to keep my carbonyl group in place right here. And then the chain that carbonyl is directly connected to, our alkyl chain, remains in place here because it remained in place up here in our template. So filling that in, we have 14 CH2 groups, CH214. We have our methyl group at the very end terminal of that, and that takes care of everything from the reactant side here that I'm highlighting right now with my laser pointer. We have copied over to here. Then we form that new bond between the carbonyl carbon of the fatty acid and our oxygen of the alcohol. So our oxygen of the alcohol I'm going to put in blue because I drew it blue over here, and that alkyl group comes over. So the alkyl group brought in 29 CH2 groups. So I'm going to plug in CH2 29 subscript there and keep that in parentheses so that we're referring to all 29 groups are CH2s. And then finally our end cap here to follow the octet rule would have to be a CH3 group. And you could write that as either CH3 or H3C. Those are equally good. And now to check our work here. If we've done this correctly, the reaction of an alcohol plus a carboxylic acid always yielded an ester back in our chapter on general chemical reactions, and that's going to be true here as well. So I check off that I have indeed created an ester.